In the last video, we have seen the net radiative heat transfer between two black surfaces, and we have seen there is a space resistance with respect to the orientation. Because of the orientation, there will be a space resistance, and it is given by 1 by A1 F12, and you have seen the net radiation heat transfer between two black surfaces is equal to sigma T1 raised to 4 minus sigma T2 power 4 divided by the resistance 1 by A1 F12, where F12 is the view factor. Now let us see what is a net radiative heat transfer from a gray surface, from the surface of a gray body. What will be the net radiative heat transfer? You have seen that radiosity is equal to epsilon times EB plus 1 minus epsilon times G. What is radiosity? This I have explained radiosity with this figure. Radiosity is the net radiation leaving the surface. It includes reflected radiation and emitted radiation. So radiosity J is equal to epsilon EB plus rho G, where rho can be replaced with 1 minus epsilon. So J is equal to epsilon times EB plus 1 minus epsilon times G. This will be the radiosity J. Now what is a net radiative heat? We are interested in net radiative heat transfer from a gray surface. This is the energy emitted by energy leaving the gray surface, not emitted, energy leaving the surface. So what is a net radiative heat transfer? This will be equal to net Q from surface is equal to area times whatever it is leaving minus whatever incident. So area times J minus G will give us the net radiative heat transfer from a gray surface. Now from this expression, from the expression of radiosity, we can replace G in terms of J. Okay, we are interested in replacing G. Okay, so G will be equal to, from this equation, G will be equal to J minus epsilon into EB divided by, this will come down, 1 minus epsilon. Okay, so this is the value of G. Now net Q will be area times J minus G will be J minus epsilon EB divided by 1 minus epsilon. Now if we solve this, we can find that 1 minus epsilon will come to the numerator, and taking the LCM, 1 minus epsilon J into 1 minus epsilon minus J minus epsilon into EB. So if we solve this, J and J will cancel. J into epsilon minus will come. This minus and minus will come plus. So this will be epsilon to EB. Area will be here. Okay, epsilon into EB minus epsilon into J divided by 1 minus epsilon. Okay, now we can take the epsilon outside. So A times epsilon into EB minus J divided by 1 minus epsilon. This will be the answer, Q net. Now this will be 1 EB minus J divided by 1 minus epsilon. Now we can equate this in analogous to the electrical conductance, like Q net as potential difference divided by resistance. Now if we express that in that term, we will get the potential difference delta B by J. This is the difference by resistance. So now this A epsilon will come down. So EB minus J divided by 1 minus epsilon divided by A epsilon. This will be the resistance. That is the resistance value. The surface resistance value will be R will be equal to 1 minus epsilon divided by A epsilon. This is the value of, this is called surface resistance. Surface resistance from a gray body, where epsilon is the emissivity of that body, whatever the body we are talking about. Okay, 1 minus epsilon divided by A epsilon. Okay, so this is the surface resistance of a gray body. Now you see, in the last class we have seen what is the space resistance. Space resistance is 1 by A1 F12, and there will be a surface resistance associated with every gray surface. Okay, that is this. There will be surface resistance associated with every gray surface. Okay, so 1 minus epsilon divided by A epsilon. Now Now if we have two gray surface, I have gray surface here, one, and I have another gray surface here, two. What will be the net radiative heat transfer? To calculate the net radiative heat transfer, we need to find the resistance in between. For example, there will be a surface resistance associated with every gray surface. So this is the surface resistance. Okay, another surface resistance will be associated with this surface, gray second surface. So this is R2, R1 and R2 are surface resistance. Then there will be a space resistance associated with the orientation. So this space resistance. So there will be three resistance when two gray surface will interact. There will be only one resistance when two black surface will interact. When black surface interact, you don't have this surface resistance. This doesn't come play. Only the space resistance will be there. When there is a gray surface, you have this surface resistance on both surface. Now I am putting one more gray surface here in between. Let's say this is the first gray surface, this is second gray surface. There is radiative heat transfer between these two. Now my objective is to put one more gray surface to see what happens. I'm putting one more gray surface in between, having emissivity 3. Okay, this having an emissivity 1, this is having emissivity 2. Okay, so there will be a surface so this is called the radiation shield. That means usually this is this is inserted to reduce the heat transfer between 1 and 3. So when we insert one radiation shield, what happens? See, we already have a gray surface, so this will have a surface resistance. This is R1 is surface resistance, and there will be a space resistance. After that, there will be a surface resistance on this surface, this side of the surface of this gray body. This is the gray body. So R3 will be there will be a surface resistance. This is space surface. So R1 and R3 will be a surface, and R2 will be space resistance. Again, on this side also we will be having a surface resistance. Okay, R4 will be surface, then there will be space, then again there will be surface. Okay, so R5 will be space, R6 will be surface. So like this it will be going on. Okay, if I put one more, now if I am putting one more radiation shield, okay, let's say imagine I am putting two radiation shield, then there will be surface resistance 1, surface resistance, space resistance, surface resistance, again surface resistance, space resistance, surface resistance, then surface resistance, space resistance, surface resistance. So total, when we are putting one shield, I am putting one shield, 3 more came in additional. When I'm putting 2, there will be 6 more, 3 more will come again. Okay, so like this it will go on. Now we have to see what happens with the radiation shield. So that I'll explain in the next video. And just right now you see right now you have to feel what is surface resistance and space resistance associated. Now you can actually do numericals on this. Okay, now for example, there are two gray surfaces. Let's say this is the gray surface with emissivity equal to 0.9, and another gray surface with emissivity 0.8. This is at a temperature of 100,000 Kelvin, then this is at a temperature of 300 Kelvin, and given they are having an orientation, and given F12 is equal to certain value 0.5, and given area is equal to so and so, area of 1, area of 2 is equal to so and so, value is given. So you have to calculate the net radiative heat transfer between these two. So Q1 to 2 you have to calculate. Now how do we calculate Q1 to 2 is very simple. You take E1 EB1 minus EB2 divided by R total R, because these are in series. This is the surface resistance. This surface resistance is epsilon 1 A1 divided by 1 minus epsilon 1. sorry, in the reverse way. This will be 1 minus SS. This will be 1 minus epsilon divided by a 1 minus epsilon 1 divided by a1 epsilon 1. Then there will be a space resistance which will be 1 by a1 f12. Then there will be again a surface resistance associated with this. This is 1 minus epsilon 2 divided by a2 epsilon 2. Okay, so this will be our three resistance will be these three will be our resistance. Okay, now what will be the Q12 means? Q12 will be EB1 will be sigma into 1000 power 4 minus sigma into 300 power 4 divided by R1 plus R2 plus R3. Now this will give us the net radiative heat transfer. Now we can see that these are in series, so resistance will add on the Q. Net heat current flow will be same in both, that is Q12 will be, this will be same, this will be Q along here and here and here, everywhere Q will be same. Okay, this is how we solve these radiation problems. Okay, we actually equate that to the electrical conductance problem, same conductance problem, and we can solve that. So that the parallel and series combination we can work it out easily. So once we find out the surface resistance and space resistance, we can find out the overall heat transfer. What is the net radiative heat transfer? Okay, we are interested in the net radiative heat transfer.